Let's go. Okay, chapter 6, classroom discussion. We have to solve some problems on work and energy. First problem, we have a piano that slides down and it's kept from accelerating by a man who's pushing back on it. Okay, so a lot of forces here right away. We have the man pushing, we have the inclined plane, so there is a gravity on the piano, and it's kept from accelerating. That means what? No acceleration. That's going to be a simplification. And we have to do the calculations of the force that is missing, the work done by forces, and the net work done as the final step. Oh, and it says ignore friction. So if it says ignore friction, please make sure you don't show friction force on your sketches, on your diagrams, because there is no friction. No friction is given. So we start with the sketch. Here's the piano. Doesn't really matter if it's a piano or whatever, it's still a particle. We're still doing particle model. And for particle model, we don't care the geometry, we don't care how heavy it is. Let's do the free body diagram with forces. First force is gravity. Gravity downward towards the center of the earth. Then normal reaction force. Normal reaction force is perpendicular to the surface. So surface is slanted, and that's why normal force is slanted as well. The piano is going downward, and for downward direction, we show velocity vector. So velocity vector shows direction of motion, and it says kept from accelerating. So acceleration is just 0. It's also a very useful statement to put on your sketch. It's not always the case that acceleration is 0, but for this particular problem, acceleration is 0. And that means no change in velocity. That's the direction for motion. And there is a man who prevents from accelerating. So clearly the force from the man on the piano should be the one that slows it down. Gravity is going to speed it up, but the pushing force will prevent it from speeding up, and that's why push force is in the opposite direction. You can think about a push force as an analog of friction. Now, for angles, we got angle theta for the inclined plane. And if this is theta, then this is 90, and this one is 90 minus theta. So the other one is theta, and you have the angle between the gravity and the y-axis as theta being adjacent. This is the setup for forces. Time to figure out the missing force. For the forces, you have the second Newton's law, and there is a normal reaction force, force of a push, and the gravity. So 3 forces, and acceleration is 0 this time. So on to y-axis. See the y-axis, it's the axis that is perpendicular to the slanted plane. And we got normal force in the same direction as the y-axis. So it's positive normal force. We got the push, which is perpendicular to y-axis. So every time something is perpendicular, that component is 0. So positive normal, 0 for the push. And for gravity, onto y-axis, it's the adjacent component. It's the adjacent side to the angle theta. And if it's adjacent, it's got to be the cosine function. And see how it's pointing downward. So it's opposite to the positive direction for y. And if it's positive, and if it's in the opposite direction, then the component is negative. So it's negative gravity and the cosine of the angle of incline for the y component of gravity equals to 0 because acceleration is 0 as given for this problem. From this equation, we get the connection between normal and gravity. So mg cosine theta is what counterbalances the normal reaction force. Moving on to the x-axis. Onto the x-axis, what do we see? We see F push is opposite to x. So if positive x is downward, push is the opposite direction. So the component of the push is negative. That's what we have right here, negative for the push. Normal force, let's take a look at the normal force. Normal force is perpendicular to x-axis. And if it's perpendicular, the component is 0. So if a vector is perpendicular, then component on that axis is 0. That's exactly what you see in this equation. So 0, take away the negative push. Now the gravity. What do we see for gravity? Gravity is gravity creates this kind of a component, and this component faces the same direction that the positive x is showing. So the component is therefore positive. And if this angle is theta, then alternate interior angle here is also theta. So we're talking about the side that is opposite to theta. And if it's opposite, then it is the sine function. So gravity produces a positive component with the sine function. That's exactly what you see on this equation. And acceleration is 0 because it is given as 0 in the first place. So second equation allows us to solve for what's missing. What was missing is the push force. It's mg sine theta. Mass is given, g is given, and sine of the angle gives this much. So it's 1600 newtons, which is quite a lot, but hey, it's the piano, right? The heavy piano that is going downwards, so you do expect quite a force in the opposite direction to slow down the piano from accelerating. So the force exerted by the man on the piano is 1600 newtons. Now work done. What is the work done? How do we calculate work done if the force is constant? It's the force, the displacement, and the angle between the force and displacement. Let's take a look at the force. The force is, up the incline, and displacement is the direction for motion. The velocity shows the direction of motion and shows the displacement vector as well. Whatever is the displacement direction, that's the velocity direction. So displacement is downward, down the incline, and the push is exactly opposite. So what kind of angle are we talking about? It's the angle of 180 degrees. So the angle is 180 degrees, and the work done is the force, displacement, and the cosine of angle. The force is now known. We just calculated it. It's 1600 with 2 sig figs, but with 4 sig figs, it's actually, a little more accurate. So you show the intermediate calculation result not the rounded one, so that error does not propagate. And displacement is 2.9. I believe it's given. Yeah, it is given as 2.9 down the incline. So displacement is given. Displacement is 2.9. And the cosine of 180, which makes it a negative result, -1. So it's a negative. And whatever the value here from multiplication you get, 4,600 or 4.6 thousand joules. Units are joules. For work done in energy, it's always joules. So this is the work done by the man on the piano. It's very important that it's negative, because negative means what? It's the energy transfer not to the system, but out of the system. It's the piano that should have been accelerating, right? It's going to gain kinetic energy and accelerate and, move faster and faster downward, but there is the force of a push from the man that slows it down. It prevents the piano from accelerating, so the piano loses its energy. And you can think about push as friction. Doesn't really matter. Friction will always steal energy from the system. So work is negative. Do not ignore the negative. You have to show that for this case, work is negative. Energy is lost by the system. The system slows down because of that force acting on it. Now work done by gravity. Let's take a look at the gravity. The force of gravity right there. And displacement is still the same as the velocity vector. Velocity shows the direction for displacement. And the angle, you can see how this is theta, this is 90. So the other angle is 90 minus theta. So the angle between the gravity and the velocity, which shows the displacement, is 90 minus theta. So for work done by gravity, you say force, gravity, mass times the g. Displacement, still 2.9 because it's given. And it's the cosine of 90 minus theta. Theta was given as 25. The incline is 25. So 90 minus 25 is 65. 65 is the reference angle for calculating the work done by gravity. I want to point out it's positive now. See, it was negative for push or any friction force. Now for gravity, it turns out to be a positive one because it's the gravity that speeds up, that accelerates, trying to accelerate the piano downward. And acceleration means increase in kinetic energy. So you have an energy transfer to the piano through the force of gravity. So positive value makes sense. And I want to point out is exactly the same as the force of a push, but with a negative sign. See how it's a negative for the push and it's positive for gravity. So you will come to a conclusion that the net force, it's the negative 4.6 thousand joules plus the gravity, which is a positive value. Oh, and we haven't discussed work done by normal force yet. What is the work done by normal force? Let's take a look. Normal force is perpendicular to x-axis, and it's perpendicular to the velocity vector. So it's perpendicular to the displacement vector. And if we have a perpendicular connection, then it's the 90 degrees angle. Cosine of 90 is 0. So what is the work done by normal force onto x-axis? It's 0, which is exactly what I'm talking about here. Work done by normal force is 0 because of the 90 degrees angle between the normal force and displacement. And overall net work turns out to be 0. And you say, how is it possible? We have also many works working, also many forces working, and the net work is just 0. Well, you have to recall the main principle for the change in kinetic energy work done. And if you'll apply this principle here, you would say what? Change in kinetic energy. How much of a change do we have? Well, we don't have any change because with no acceleration, there is no change in velocity and no change in mass. And 1/2 is still 1/2. So change in kinetic energy is 0. And the work done, the net work done, should also be 0. And that's exactly what you get from the calculations. The net work is 0. Change in kinetic energy is 0. So we haven't violated any principles while doing the calculations. So this is a perfect example when you have dynamics in place, and then you can apply the change in kinetic energy work done theorem and calculate for something that's missing. Sometimes some of the parameters would be missing, so the only way for you to solve this problem would be a change in kinetic energy work done principle anyways. But if you can do dynamics in the first place and figure out the missing forces, that's good. That will save you some time as well. So yeah, that's the problem. Moving on to the next one. We got a car that is increasing its speed by 50%. By what factor will the braking distance increase if everything else is the same? This is a very good problem because nothing's given, right? And yet you have to answer a question. It's one of those beautiful problems when you really don't need many things to be given, and you will still be able to answer some questions, and there's a lot of good analysis behind this. So let's take a look at the car that is trying to brake and slow down, and you have the friction force, of course, because it's the only force that can slow you down on the freeway. We got gravity downward, we got normal reaction force from the freeway onto the car, and it's perpendicular to the surface. And there is a friction force slowing you down. That's the net force. And net force shows the direction for acceleration. And it's indeed the case because we're slowing down, velocity is to the right, acceleration is opposite, and we are slowing down with that rule in mind. With no parameters given, the only way to do the analysis is the work energy theorem. So the change in kinetic energy is the work done. That's the overall approach. And it's the work done by friction that matters because work done by gravity onto horizontal displacement is 0. See how gravity and displacement are perpendicular to each other, so 0 work from gravity. Normal reaction force versus the displacement also perpendicular, and you have 90 degrees, cosine of 90 is 0, so work done by normal force is also 0. So it's the friction force that does work that is non-zero, and once you calculate the work done, we can do some comparison and analysis between the distance that the car travels before coming to a stop. Let's see what we can get from the second Newton's law first. We got normal force, negative gravity. Normal is positive, gravity is negative, friction is perpendicular onto y, so friction is 0 onto y axis. And acceleration is also perpendicular to y-axis, so it is 0. So 0 to the right side, and we got normal force being exactly the same as gravity. And that's what you can substitute for the normal force value in order to calculate the friction force. Friction is mu times normal force, and normal force is the same as gravity, so substitute gravity into normal force and get the mu mg expression to calculate the friction force. Friction force is mu mg because it's mu times the coefficient of friction times the normal force, and normal force is gravity. And the work kinetic energy principle says work done, change in kinetic energy, and work done by normal force is 0. Work done by gravity is 0. Once again, both forces are perpendicular to displacement. So 90 degrees here, 90 degrees there. Cosine of 90 is 0. Work done is 0. So it's only work done by friction force that matters for change in kinetic energy. It's only the friction force that can slow you down and change your kinetic energy. And how do we calculate work? It's the force, displacement, and the cosine of angle between the two vectors. Force of friction is one way, displacement is opposite. So what's the angle between friction and displacement? It's 180 degrees. Displacement is to the right, friction is to the left. So it is cosine of 180 degrees, which makes it a -1. So it's a negative. Force of friction, we just figured out that force of friction is mu mg. So we substitute mu mg for friction. Displacement is displacement. And this is the change in kinetic energy. Change is always final, take away initial. Change is always final, take away initial, which means 1/2 m final velocity squared, take away 1/2 mv initial squared. Now we eventually come to a stop, so final is just 0. So your change in kinetic energy is just 0, take away 1/2 mv initial squared. And I want to point out that the right side is negative and the left side is negative. See how both negatives came up, and now you can cancel them. You can multiply both sides by -1. And that's a perfect step to get rid of negatives. But you can't ignore the negatives. You can't say that work done is just mu mgd. You can't say it's not negative. It's negative. Negative is still there. And changing kinetic energy is also negative. We're slowing down. We're losing kinetic energy. And kinetic energy decreases. So it's not only valid math-wise, it's also valid physics-wise. You got both sides of the equations being negative, and now you convert them to positive because you can multiply both sides by -1. And what's even more important, mass cancels. You have mass on one side, mass on the other side. The mass of the car does not matter. And we already had this phenomenon before. We discussed that confirms our particle model. It doesn't matter how heavy the object is. It's only the coefficient of friction that matters. And you can see, once again, it's only the coefficient of friction that really matters on the distance traveled that the car comes to a stop. So final result for the distance traveled from this expression is initial velocity squared divided by 2 g and the mu, the coefficient of friction. Now, the question was, how much will the distance change if the initial velocity is 50% more? Well, 50% more means 1.5, the coefficient of 1.5. And then you have to square that, because see how velocity function is squared for the distance traveled, and squaring 1.5 gives you 2.25. So your distance would be more than double. If it takes, say, 100 meters for you to slow down from, say, 50 meters per second, then you double the velocity to 100 meters per second, then the distance is not going to be 100 anymore, it's going to be 225. So doubling the velocity would produce quadruple distance. This is the connection. The connection is squared. You have distance depending on the initial velocity, and its velocity squared. That's the function. And the rest is constant. You might say, hey, what about 2g and mu? Well, g is just a constant, and mu is also a constant. It's a coefficient of friction. If the conditions are the same, then it's just v squared, the initial velocity squared, that defines the distance for coming to a stop. What's the moral of the story? You have to be careful with your initial velocity. The faster you go, the more time and the more distance it's going to take. So it's either you're safe or you go into an accident. That's not good. It's good how, like I said, nothing's given, only the increase of 50%, but then you can still do quite an analysis about the braking distance just by using basic dynamics and the change in kinetic energy work done principle for your benefit. Keep in mind that work done by friction is always negative. Keep in mind that change in kinetic energy can be anything, but kinetic energy by itself, it's only 0 or positive. But the change can be negative. See how change in kinetic energy can easily be negative too, and then you have negative on both sides. Okay, next problem. It requires 6 joules of work to stretch a spring by 2 centimeters. How much more work will be required to stretch additional 4 centimeters? First of all, be careful. We have centimeters. You cannot do centimeters. You have to do meters. And joules are good. Joules are good units for work. It's positive work. What's so special about positive work? It means that there's an energy transfer to the spring. You do work on the spring. Spring gains elastic potential energy. So we know how to calculate it, 1/2 kx squared. So let's do that. We have the unstretched position, then unstretched position, then we have a little bit of stretch. How much? 2 centimeters. Convert that into meters. And then finally, we stretch it, additional 4 centimeters. So now we are at 0.6 meters. And the question is, how much more work is needed to do so? Well, work done is 1/2 kx squared. And that's the formula we got from lectures. Work done is the change in potential energy. K is the stiffness, and X is either compression or stretching. So from this definition, you can calculate the stiffness of a spring, because it's given that you have 6 joules to stretch 2 centimeters. So multiply both sides by 2, divide by delta x squared, you get 30,000 well, you don't do joules per meter squared. You have to convert into newtons per meters. But dimension-wise, from the equation itself, you get joules per meter squared. And the final state, when it's stretched to 6 centimeters, it's the same spring, so it's the same stiffness. You got to understand that this stiffness thing is constant. Once you figure out the stiffness for the spring, no matter what you're going to do with that spring, that stiffness is going to stay constant. And that's exactly what we have here. We just found the stiffness, and now we're going to use it to solve for other conditions for the same spring. It's the same stiffness. So 1/2 kx squared, 1/2, same k, same stiffness, and new elongation or stretching or compression squared gives you 54 joules. But the question is not for 54. The question is how much more. Be careful reading the question. How much more means you start with what you had at 2 centimeters and now what you had at 6 centimeters. So 54 is the final state and 6 was the initial state. So how much more? You need extra 48 joules because it's the change, it's the amount between the final and the initial. So 1/2 kx squared is the formula. And sometimes you will need the Hooke's law to figure out the stiffness. This time we don't need it because you can just you can just calculate it from what's given. But if you can't do it from 1/2 kx squared, you can do it from the Hooke's law, which is the spring force as negative k times delta x. Okay, on to the next problem. Okay, here we have the roller coaster, and this time there is no friction. For no friction case, you say k plus u equals k plus u, and that's pretty much it. You don't need to say change in kinetic energy work done theorem because there's no friction. You got all the geometry given, all the heights, and you have to figure out the speed. The speed is a part of kinetic energy, so there's going to be a connection between kinetic energy and potential energy, and the sum total stays the same because of the conservation of mechanical energy. So no friction means mechanical energy is conserved. So your total mechanical energy at point 1 is the same as total mechanical energy at point 2, is the same as total mechanical energy at point 3, and is the same as total mechanical energy at point 4. So K1, U1, K2, U2. K1 is 0. Why is that 0? Because we start from 0. That's what it says. It's given that at point 1, velocity is 0, so kinetic energy is just 0. And it's all gravitational potential. And then it reaches the point 2. Point 2 is the 0 location for gravitational potential energy. So potential energy at point 2 is 0. It's just given. That's what we take our 0 level for. So your kinetic at point 2 is potential at point 1. Mass cancels again, and you solve for how fast it goes. Radical 2 g y sub 1, and plug in the values that are given. Y sub 1 is given. It's 32 meters, and it's going at 25 meters per second. Makes sense for a roller coaster. If you want to convert from meters per second to miles per hour, you roughly double it. You multiply by 2. So 50 miles per hour, well, it's fast, but yeah, it's always going fast at the bottom at the roller coaster. So yeah, makes sense. It is expected. Then it's the first versus the third point, k plus u equals k plus u. The first one was the 0. And for gravitational potential energy for point 3, we have 26 meters. It's given. It's right there at point 3. You are at 26 meters. So you still have some kinetic energy. Oops. You still have some kinetic energy and some potential as well. So you're going to go slower. It's you go uphill, you slow down. So at point 3, the calculations show that you'll be going at 11 meters per second. Calculations are exactly the same as before. You can see mgy and 1/2 mv squared are the only formulas we use for calculating kinetic and potential energy. So mass is canceled, and we are going slower. It was 11. It was 25. Now it's 11 once you reach point 3. Makes sense. Now for point 4, what do we have? Let's take a look at point 4. We are giving up some potential and speeding up. We gain some kinetic because we are a little closer to the ground, and we're going to move faster than at point 3, but still slower at compared to point 2. So number 1, all potential. Number 2, all kinetic. Number 3, little bit of both. And number 4, also a little bit of both, but more kinetic than potential. So for the last point, same calculations, 1/2 mv squared and mgy. And calculations give you 19 meters per second, which is, like I said, more than 0.3 and less than 0.2. So also makes sense. So the roller coaster with no friction is an easy peasy problem with just k plus u equals k plus u all the way and nothing else. See how there's no dynamics, no vectors, just pure analysis of kinetic versus potential energy, which is a benefit from conservation of mechanical energy because no friction is present. Same problem, but now we got friction. Force of friction equals to 0.23 of its weight. That's what's given. So what would be the speed at 0.2? And the distance traveled is also given. So everything is given. It is time to say we can't do k plus u equals k plus u anymore because part of mechanical energy will be converted into thermal energy. There will be friction. There will be, you will lose a little bit of mechanical energy, gain in thermal energy. Overall energy is still conserved, but mechanical energy is not conserved. Point 2 would be the 0 gravitational potential energy level because it's the lowest point. So point 1, all potential. And a little bit of kinetic as well. See how we don't start from rest. This time there is a little bit of kinetic energy for point 1 as well. So kinetic plus potential here, all kinetic there, and we have some losses due to friction. That's the energy balance. And once again, a friendly advice, if there is friction, do not do energy balance, but rather do the change in kinetic energy, work done principle. You will never make a mistake with that approach. So what is the work done? We got the friction, we got the gravity, and we got the normal reaction force. Once again, normal reaction force is just 0 work because it's perpendicular to direction of motion. 90 degrees, cosine of 90 is 0, and you get 0 work for normal force. The work done by gravity is the negative of a change in potential energy. You have to keep this in mind. For any kind of change in potential energy, it's the negative of the work done by this conservative force. It's a very handy and useful connection. that you will solve for many different scenarios. This comes out naturally from the definition of potential energy. And the only drawback here is that you do have a negative for this connection. Work done by a conservative force is a negative of the change in potential energy that it produces. Change is final takeaway initial. That's the change. And then there is still a negative in front, that change. So there is a negative, and you end up at the zero level because we are at point 2. The final is just 0. So it's 0 for the final. Take away the initial. The initial is mg y sub 1. Y sub 1 is given as 32 times mass times the g. See how it's a negative of a negative, and it makes it positive. So this negative in front of the paren is very important because it allows you to calculate potential energy in the proper way, being positive value. If this is the 0 level, then everything above should be positive. And that's exactly what you get from this equation. mgy, this is how you calculate the gravitational potential energy at the top. And with that gravitational potential energy, you have the work done by gravity, which is a part of the work done change in kinetic energy theory. Force of friction. Force of friction is doing work as force times displacement times the cosine of angle between. It is given that the force is 0.23 of the gravity. It says specifically that it's 0.23 of its weight. Weight is mg, so 0.23 mg. That's what you get for the force. Displacement is given. Displacement says 45 meters that is traveled. And once again, friction is one way, displacement is the other way. You have opposite direction for two vectors. You have 180 degrees. Cosine of 180 is -1. So work done by friction is negative. But it's not a problem. Once again, the work done is just added up. And if you're adding up something that is negative, you just subtract it and you will never make a mistake. If you're going to do energy balance, then you still have to add it. Even though it's a negative, you still have to add it for the energy balance. And that's the confusing part. So I suggest you never do the energy balance. You do the change in kinetic energy work done theorem principle, and you'll never make that mistake. So force, displacement, cosine of 180 gives you the negative. That's the force, and that's displacement. This is the work done by friction. So time to add up all things together. You got work done by gravity. You got work done by friction. You got work done by normal force. And that's the change in kinetic energy, which is final takeaway initial. It's very easy to add them up. No confusion on what to do. Kinetic is always a non-negative number. Kinetic energy, it's everything is easy and straightforward with this approach. Fun fact, mass cancels. Mass still cancels out. You factor out the mass, you cancel it on both sides. You don't care how heavy the card is. The speed is still a function of how high you go in the first place, how much of a distance you travel for friction, and how fast you are going in the first place. All things considered together, you get 21 meters per second, which is less than before. Remember the previous problem? For point 2, we had 25 meters per second, which we traveled faster. Now it's only 21 meter per second. That is slower. Why is it slower? Because there is friction. Friction slows you down and you lose your mechanical energy. You transfer that mechanical energy into thermal energy. Makes sense, right? Yeah, that was the problem. So two like conditions are similar. I mean, the problem by itself is the same as before, but this time we have friction. And now you see how you tackle this friction problem with not a K plus U equals K plus U, but rather the change in kinetic energy work done theorem. Okay, one last problem. It's the power problem. See, the car generates 18 horsepower. We should never use horsepower for calculations. And you're traveling at certain kilometers per hour, which is also not a system international unit. So you really want to do some conversions before even doing any calculations. That's for sure. So what's the force? Due to friction and air resistance. So we have to draw a sketch and draw the forces. This is the car, gravity pulling it down, normal reaction force from the freeway. Then there's a force that propels the car forward. The internal combustion engine generates a certain force. And then there is the drag force that we are looking for. The question is for what's the force due to friction and air resistance. So this is your total force that slows you down. And you travel in the rightward direction. Velocity is constant, so there's no acceleration here, and it's to the right. So that's what's given. And your horsepower, this is the conversion factor that we haven't discussed in lectures, but now you have it here in the classroom discussion. 1 horsepower is approximately 746 watts. Remember, those watts are joules per second. This is how much energy is transferred to or from a system per unit of time. So 746 watts. Horsepower disappear, you multiply by 18, and the total amount of watts, the total power from the engine is about 13 kilowatts, 13,000 watts and some change. This is what's given. Now, what is power? Power is the work done with respect to time, or energy transfer with respect to time. And definition for work, if it's constant, you calculate it as force, displacement, and the cosine of angle between the two vectors. So if you plug in this definition for work for the power, you will see that it's force, and then it's displacement versus time. And what is displacement versus time? How do you calculate? What is the parameter that defines displacement with respect to time? It's velocity. So instead of force, displacement, and time, you can say it's just force times velocity. So your power, the instantaneous power, if you will, at any moment of time is just the force, the net force that you have, and the velocity, how fast you go in a certain direction. So this little trick allows us to solve for the force right away. So it's just power divided by velocity. Especially if velocity is constant, you don't have to bother with calculus. And we do it. We do the calculations. We got the power given. Velocity must be converted to System International, of course, 95 kilometers per hour. You multiply by 1,000, divide by 3,600, and eventually you get to 500 newtons and some change, which is reasonable for a car that is traveling in a certain direction. There is a little bit of a drag, and that slows the car down with all the resistances and friction. That's it for this chapter. I really want you to focus on the same roller coaster problems. They look the same, but see, the approach is different because you have friction for this one and you don't have friction for the previous one, which makes it a easier calculation. K plus U here, and no K plus U, but rather the change in kinetic energy work done theorem for the problem that has friction. Give it a try. You can also do it with energy balance. Give it a try with energy balance, but chances are you're going to make a mistake while adding or subtracting work done by friction. If energy balance makes more sense, go ahead, do it. You'll get full credit either way. Okay, stop recording.